Now that we've covered all three of Newton's laws, you're ready to move on to a problem that encompasses all of the concepts. So for this problem, imagine that there's a rocket sitting in outer space, and it's far enough away from everything that we can ignore gravity, and it exerts a force of 1,000 newtons on its propellant going in the backwards direction. And if it weighs, we'll say 50 kilograms, it's a small rocket, what is its acceleration going to be, and in what direction? And you're going to have to use a combination of Newton's third law and Newton's second law to try to figure this out. So good luck, pause the video, take some time to work this out, and then we'll resume. Hopefully all of you had some idea of what's going on there. If not, pay attention, we'll figure it out together. So it's exerting a force of 1,000 newtons backwards on its rocket propellant. Now every action has an equal and opposite reaction. And the opposite reaction of the rocket exerting the force on the propellant is the propellant exerts the same force on the rocket, which is 1,000 newtons in the forward direction. And once we know this, then we can use F equals ma to figure out the rest. Force is 1,000 newtons, mass is 50 kilograms, and acceleration is unknown. And once again, we've defined the direction going in the right-hand direction as positive, and this is just convention. You can do it either way, but it's important to keep track of which way you're doing it. So 1,000 newtons over 50 kilograms equals acceleration. We just divided through by 50 kilograms. 1,000 divided by 50 is 20, and newtons per kilogram is meters per second squared. So acceleration is 20 meters per second squared. Now let's do a slightly trickier version of this problem. Imagine that the rocket, we still know it's 50 kilograms, and this time we're saying it's ejecting 20 kilograms of fuel out the back with an acceleration of 10 meters per second. 20 kilograms of fuel, and it's accelerating at 10 meters per second squared. Now try to figure out what the acceleration of the rocket is. And don't worry about the changing mass. We're just going to ignore that for now. It's a little bit tricky. So take a second, pause the video, figure this out, and then we'll go through it together. So first, we have to figure out what the force being exerted on the fuel is. And we know that F equals ma. So here all we have to do is multiply together the mass and the acceleration. And we end up with 10 times 20, and that's kilograms meters per second squared. And kilograms meters per second squared is newtons, so that's 200 newtons. So the rocket is exerting 200 newtons of force, and it weighs 50 kilograms. So now we can go back and once again do our F equals ma calculations. 200 newtons equals 50 kilograms times acceleration. Divide through 200 divided by 50 equals 4. And newtons divided by kilograms is meters per second squared. So the acceleration is 4 meters per second squared. Now we want this rocket to accelerate the same as it did last time. Either it's going to need to eject more fuel, or it's going to need to accelerate the fuel more. So as you can see, by combining all three of Newton's laws, we're able to get a good picture of what's going on with the rocket. We can use the second law, F equals ma, to figure out what's going on and how much force the engine's exerting. Then we can use the third law to see how the rocket's exhaust pushing backwards pushes the rocket forwards. And then we can use the second law again to figure out what the acceleration of the rocket itself is. Now, there's a lot of complicated stuff that we could have dealt with here. This is a bit of an oversimplification. But for the kind of physics we're doing right now, this is very accurate and very good. And we can, assuming that all of this is true, we could indeed say that the rocket is accelerating at 4 meters per second. Hopefully you understood that. If not, go back and watch it, and if you got it, you're ready to move on to the next video.